Now, in our last segment for this fourth lecture, we'll talk about Bayes' rule. And ultimately, Bayes' rule is designed to allow us to revise our beliefs, to change our understanding, our predictions for an A sub I, again, one of those partitions, given that a B, an event B, has already occurred. So if we were to find the probability of A sub I given B, looking back at all of our examples from before, then ultimately what we can do is use stuff that we've already identified. We can say that the probability of A sub I given B is ultimately just equal to this equation. And we're not going to spend a ton of time on derivation here because the derivation should be pretty apparent. It's the probability that A sub I occurs given that B has already occurred, right? That's what we're trying to find. But the probability here is just the probability that A sub I occurs and that B conditioned on A sub I occurs. Again, that's just the probability of traversing a single path divided by the probability of all of the paths where B occurred, which we derived in our previous lecture as the total probability theorem. And you should recognize this equation here. It's the sum over all j now, so that we have something different from the I. But the sum over all j of the probability of A sub j multiplied by the probability of B conditioned on A sub j. So all we're doing with Bayes' rule is saying take our specific partition relative to all possible partitions, the total probability theorem, to find the probability of A sub I given that B has occurred. So again, like I said, that's about all the further we're going to go into the derivation of Bayes' rule because it is fairly simple to arrive at. And so armed with this equation, let's go ahead and look at an example. So we're going to go back to the same one we used for the total probability theorem. But let's assume that a bowl has 3 apples and 4 oranges. Bob selects a fruit, then Steve selects a fruit. But let's ask a different question. If Steve selected an orange, what is the probability that Bob already had selected an orange? We're asking the question the other way around. Bayes' rule is really cool that it gives us the ability to look into the past to determine the probabilities of the past. So in this case, let's recall some of what we figured out on the previous slide. We had the probability of Bob picking an apple, and that was equal to 3 out of 7. We had the probability of Bob picking an orange, and that was equal to 4 out of 7. We had the probability of Steve picking an apple, given that Bob had picked an apple, and that was equal to 1/3. We had the probability that Steve picked an apple, given that Bob picked an orange. That was equal to 1/2. And then finally, we had the probability overall that Steve picked an apple, and that was equal to 3 out of 7. So armed with those, let's go ahead and look at what we really are asking here with Bayes' rule. And that is that the probability, in this case, we're asking of Bob selecting an orange, given that Steve selected an orange, is equal to the probability, in this case, A sub I. That's our Bob selecting an orange. And we know the probability of Bob selecting an orange was equal to 4 out of 7. So this is going to be 4/7 multiplied by this probability here, the probability of B, in this case, the probability of Steve selecting an orange, given that Bob selected an orange. Now, we hadn't previously calculated the probability of Steve selecting an orange given that Bob selected an orange, but we can say that it's just the complement of Steve selecting an apple given that Bob selected an orange. So in this case, it's 1/2 or 1 minus 1/2. So 4/7 times 1/2. And then we need to find the total probability theorem, which is the probability ultimately that Steve selected an orange. But if we go through and do this as the sum, then we would find that this is equal to the same probability up here, this 4/7 times 1/2, added to the other probabilities. So this is now going to be the 3/7, the probability of Bob selecting an apple, multiplied by the complement of this value here, saying that Steve selected an orange, given that Bob selected an apple. And that would be 2/3. So plugging all of these values in, you guys can do that on a calculator if you'd like, but we'll find that this is equal to 1/2. Again, it's just number crunching at this point. So what have we just done? We've gone back and said, what is the probability that Bob selected an orange given that Steve did? We're looking at the past. We're saying Steve just selected an orange. What happened a few minutes ago? Did Bob pick an orange? How likely is that? So Bayes' rule gives us that ability to look out of all the possible outcomes, what is the probability then of taking that and looking at the past, determining what caused it to occur. Now, before we jump too much further in this, I do want to take a moment and help you see that there is a different form of this equation that's a little bit simpler to look at, but a little bit less insightful as to what's going on. And that is that the probability of A sub I given B is equal to still the probability of A sub I multiplied by the probability of B given A sub I. But this is over the probability of B. Now, the probability of B here, as you may recall, this equation was the total probability theorem, and we said that that is the probability of B. And this equation is often what you'll see for Bayes' rule, not this overly complicated version that we have down here. But both of them are just as valid. They both give you the same information. And what you'll notice right out of the gate is that Bayes' rule, when you're working with total probabilities, gives you the option to change the condition. We have moved now from knowing the probability of A and the probability of B, as well as the probability of B given that A sub I occurred, to now being able to say, given the ability to collect the probability of a future event, what was the probability of the past event? What was the probability of A sub I given B? So to kind of recap, while it's kind of a simple equation or easy to arrive based on the information we've already acquired throughout this lecture, Bayes' rule really gives us a systematic or an equation-based approach for incorporating new evidence. If we have evidence that we can see in front of us, we can go back and look at what's already occurred. So Bayesian inference is something that we'll probably look at towards the end of the semester, though not in great detail. But it allows us to ultimately take models of the real world and then draw conclusions as to the causes of an unobserved event. So if we know that an event occurred, we can go back and look at the things that we didn't observe that caused it. So this really comes back to the essence of probability, which is where it fits in the picture of designing a system. We have this real world here, and from the real world, we get data. And that data helps us with inference, being able to infer things from that data. And that's really the study of statistics. Then we take that statistical data and we create models. Those models, the statistical data informing what we think are our probabilities, the likelihoods of something occurring. We then use probability theory to analyze all of that and make predictions or even decisions off of that probabilistic system, that probability theory. And that ultimately feeds back into the real world, where we can say, hey, based on the probability of such a thing occurring, what does that mean in the real world? And based off of that, we can then collect more data and end up in this vicious cycle forever if we really want to spend all day doing math. But taking a quick step back, there's two key elements in here that I want to look at. And the first is the model. And so the model is the model of the world under different beliefs. This is saying for each A sub I, we can find the probability of a B. For each different cause, what is the probability of some eventual outcome, right? For each of the different ways that something could occur, what's the total probability that we reach a certain point? Now, on the flip side, there's inference. And inference is the opposite of that. It's drawing conclusions about causes. We're saying, hey, given that we know something already occurred, what is the probability of each of the respective causes being what got us to where we are today? So let's say that we're looking at a garden, for instance, and we know that there are plants that are growing in the garden, but there's nothing around the garden right now. We don't know whether it was natural sunlight or ultraviolet lamps or what other option of providing light to those plants was used to get them to where they're at. But we can use data that we've collected from other systems to estimate. Maybe we say that plants that are under an ultraviolet light as opposed to direct sunlight only grow half as tall. And in that situation, we can look at the height of the plant, some statistical data, right? Something coming from the real world into that statistics model and say, based on the fact that this plant is 13 inches tall when it's normally 7 inches tall in direct sunlight, there's a significantly higher probability that this was under an ultraviolet light instead of under direct sunlight. Again, just an example of what you can use when you put statistics and probability together.